See overfitting collapse on a tiny Python example. By the end, you will have two fitted models, measured training and test mean squared error, and a clear intuition for why a more complex fit can hurt on new data. You will see a naive baseline, a straight line, and a cubic that perfectly matches the training points. You will also see how each model behaves on a single unseen point. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Understanding overfitting matters because we care about generalization. The core metric we use here is training and test mean squared error, which is the average squared difference between predictions and true labels. The main trade-off is flexibility versus stability. A very flexible model can fit noise, and so it risks large errors on new data, which costs you real-world performance. At small scales, a single extra degree in a polynomial can change predictions dramatically. The intuition is simple. Use a low-complexity model when you want stability. Use higher complexity when you need to capture real signal and you have enough data. High complexity shines when you have many observations per parameter. Its limitation is that with too few points, it memorizes noise instead of learning the pattern. We will build a tiny dataset of 4 training points, then 3 short experiments that show baseline, linear fit, and a cubic that interpolates. You will watch how each model scores on the training examples and on one held-out test point. First, we compute a naive baseline to set a reference. This snippet computes a naive mean baseline error on tiny labels. It predicts the same constant value for every input equal to the average of the training labels, then computes the training mean squared error, which is the average of squared differences between that constant and each true label. The purpose is comparison. A mean baseline shows how hard the task is before any model does work. If a model cannot beat the mean baseline on training error, it is not learning useful structure. This step also highlights scale. On tiny datasets, the baseline is often surprisingly competitive. Next, we fit a straight line to the data and report its fit. This snippet fits a least squares line and reports its training mean squared error. Least squares means finding the line that minimizes the sum of squared residuals on the training points. And training mean squared error is reported to quantify fit quality. This model has low complexity and can reduce error when the underlying trend is roughly linear. Compared to the mean baseline, a linear fit can capture slope information and usually lowers training error. With more data, the linear model's estimates become more stable. If you had a tuning knob here, it would be regularization strength, which trades off match to training points versus smoothness. Now we fit a more flexible model that can exactly pass through every point. This snippet fits a cubic polynomial that can exactly interpolate the 4 training points. A cubic has 3 degrees of freedom beyond the intercept, and so it can wiggle to pass through each training pair, which often drives the training mean squared error to nearly 0. That perfect interpolation looks attractive, but it is a red flag for overfitting in tiny datasets. The adjustable parameter in this family is the polynomial degree. Increasing degree increases flexibility and can reduce training error, while decreasing degree makes the model simpler and typically increases bias but improves stability on unseen data. Next, we test that flexible cubic on one unseen point to reveal its generalization behavior. This snippet tests the cubic on one unseen holdout point to reveal overfitting. It computes the cubic's prediction at the held-out input and compares it to the true target, reporting the test squared error for that single case. When a model interpolates the training points, its curve can swing wildly between them and give a poor prediction on the holdout. That discrepancy shows exactly why near-zero training error does not guarantee good performance on new data. The result emphasizes variance. The cubic's accuracy can collapse with just a small departure from the training regime. Finally, we evaluate the simpler linear model on that same holdout point. This snippet tests the simpler linear model on the same holdout point and computes the test squared error for direct comparison. Even though the linear model had higher training error than the cubic, its prediction on the unseen input is often closer to the true value, yielding lower test error. This demonstrates the bias-variance trade-off in practice. A model with a little bias can be preferable if it has much lower variance. The comparison shows why you measure both training and test error, and why cross-validation or holdouts matter, even in tiny examples. Recap: overfitting is when a model fits noise and fails to generalize. Use simpler models when data is scarce, and higher complexity only when you have enough examples. Caveat: a model that fits training perfectly may still perform worse on new data. Next step: tune the polynomial degree with cross-validation to balance bias and variance, and pick the model that minimizes average test mean squared error. If AI Foundations in Python help you, subscribe and watch the AI Foundations videos.